So this is a video about circular motion, what we're going to call uniform circular motion. And to start with, I have a question for you. If you are swinging something, it can be anything, at a constant speed, I know you can't see all of it, it doesn't matter, but if I'm swinging something at constant speed, is that thing accelerating? So is my two-factor fob, is this accelerating if it's moving in a circle at constant speed? It doesn't matter if it's a big circle, it could be anything, you know, it could be a flat circle like this, a small one. Any circle at constant speed, is it accelerating? So what's the answer to that? Well, let's think about it. We talk about acceleration, we define it as being the change in velocity over the change in time, or if we're doing calculus, the derivative of the velocity with respect to time. So, well, okay, with respect to time, so there's just a certain amount of time. So let's say the time for one time around, one revolution, is the velocity changing? If the velocity is changing, there is acceleration. If the velocity isn't changing, no acceleration. Is velocity changing? Well, let's take a look. So, as I swing this in a circle, think about the fob. So, I'm trying to go slow here. So it starts here, it goes there, it goes there, it goes there. What's its velocity, let's say, right at the bottom? Well, it's trying to move in that direction. So the velocity is this direction. When it's here, the velocity is that way. That way, that way. It's always tangential to that motion. The velocity is always tangential. So does that answer our question? Well, I said it was at constant speed. So if something's moving at constant speed, how can it have acceleration? Well, we got to go back to the definition of velocity. Velocity is a vector that represents something with speed and direction. So there is acceleration in circular motion. So for uniform circular motion, we do have accelerating motion because the velocity is changing direction. So it's accelerating motion, velocity is changing direction. We'll just do that. So what we have is some sort of acceleration, and we give that acceleration a specific name for circular motion. We call it the centripetal acceleration. And the way I remember it, because you've heard a different word that I don't like, that we won't use because it doesn't exist for what we do in this class. The way I remember this, centripetal, petal of flowers. I like flowers, flowers are good. The word that I don't want you to use is centrifugal. And if you've ever thought about a fugue state, it's a depressive state. Fugue is bad, flowers are good. That's how I remember it. So centripetal acceleration. So there is acceleration in circular motion. And if it's uniform circular motion, which means that we're talking about a constant speed, then we have some really interesting things that happen. Now, what direction is this? We talked about the velocity changing direction. The velocity was always tangential. And so if the velocity is tangential to the motion, so it always points along the tangent line, tangential. What's true about the acceleration? I'm not going to go through the full derivation right here, but I will get you a link to the derivation of the direction of the acceleration. All it is going back to the idea that the acceleration is the change in velocity over the change in time. And if you do the vector, so all you have to do really is just vector 2, velocity 2 minus velocity 1 as vectors. That'll give you the direction of the acceleration. We can think about it mathematically like that, or we can actually think about it in this kind of situation. Think about it conceptually too. So if I'm swinging this in a circle, what's keeping it moving in a circle? What is the thing that is keeping it moving? Well, it's attached to the lanyard. So I've got this lanyard here, and that's the thing that's keeping it moving in a circle. What direction is the lanyard pulling on it? So let's think about this conceptually. If we've got the fob moving in a circle, and let's say that it's moving this way around the circle, we figured out that the velocity is tangential because at this moment it's pointing that direction. That's the direction it's moving. So velocity is tangential. And what is causing it to accelerate in a circle, or to move in a circle? Well, it's the lanyard. What direction is the lanyard pulling on the fob? Well, when the fob is here, what direction is the lanyard pulling? Well, the lanyard's pointing that direction. That's the only way it can pull. Strings can't pull in any direction except the direction that they're in. So when the fob is here, the lanyard is pulling this way, which must be the direction of the acceleration. When the fob is here, the lanyard's pointing that way. Same thing here. So what we see is the thing that's keeping it moving in a circle, the thing that's, it's a net force, which causes an acceleration, a centripetal acceleration. We see that that acceleration always points into the center of the circle. So mathematically, I'm not going to do that here. Conceptually, you can see that, well, this has to be the thing that's causing it to move, to change direction. So we've got this for circular motion. So the velocity is tangential, and the centripetal acceleration, which I usually label as 8c, is always towards the center of the circle. Always towards the center of the circle. And these two things right here, those are absolutely key for circular motion. So the one thing you need to absolutely remember from this video, centripetal acceleration points towards the middle of the circle. Velocity is always along the direction of the motion, so it's tangential to the circle. So very, very important. Well, let's think about some other things. What else can we figure out about circular motion? You know, we talk about velocity, but what does velocity mean in a circle? Well, we need to go back to the definition of velocity. So what I'm going to do is go back to, just like we went to the definition of acceleration here, let's go back to the definition of velocity. All right, so what is the definition of velocity? Well, velocity we define as the change in position over change in time, or the derivative of the position with respect to time. So let's think about what that would mean in a circle. If we have something moving in a circle, and let's just say it's going this direction, we can think about the velocity as the change in position in time. How far has it gone in a certain amount of time? Well, let's figure that out for some time, okay? So what would be a reasonable amount of time to talk about if something's moving in a circle? What would you guess? Think about it. The time it takes to go one circle? If you thought that's a good bet. If you thought of something else, that'd probably work too. The one I'm going to work on is the time it takes to go once around the circle. That time has a special name. And unfortunately, it's reusing a label from something else. We define the period as the time in seconds, so its unit is in seconds, for one revolution, to go once around a circle. All right, so the period, which labeled is capital T, so we have to be really careful because we've been using this as tension usually, so gotta be careful. Capital T now could mean tension, it could mean period. You have to watch the units and think about what it's saying, so think about what that T means. So the period is the time in seconds for one revolution. How much time does it take to go once around? Alright, velocity is the change in position over change in time. How far has this object gone if it goes once around the circle? How far has it traveled? If you were to walk around a lake, once around a lake, how could you figure out how far you have walked? Well, if it's not a nice circular lake, we know something about the distance around. We have a special name for that. It's the circumference. So, the distance traveled in one revolution is one circumference, and we are going to have the time it takes. The time we define as that period, capital T, and what is the definition of the equation for the circumference of a circle? And now you're going, it's got pi and it's got r in it. This is a linear distance. Its unit has to be single meters. So if your brain goes to pi r squared right away, pi r squared is meters squared. That can't be the right one. We must use the other one. So what's the other one? 2 pi r? You remember that? 2 pi r. So the velocity when we're talking about something moving in a circle is 2 pi r, which is the distance traveled, one circumference, over the period, which is the time to go one circumference. And so we've got this definition of velocity that we can use. And then what we can do is connect this up with this connection, and we actually come up with the definition for a definition equation for the centripetal acceleration. So the centripetal acceleration, we define it as v squared over r. So it's the speed squared, and we're using v, but remember v, speed, velocity. I'm going to talk about it as velocity, but remember the direction is changing. So mostly we're going to be talking about the speed with these equations. Speed squared over the radius. So I want you to think about two things now. If the velocity gets bigger, what do you think happens to the acceleration? So think about that. So if I'm spinning something slowly, it has a certain amount of acceleration. Oops. If I spin it fast, do you think that has more acceleration or less acceleration? Well, if we look at the math, if this gets bigger and it's on top, that should get bigger. And that's probably conceptually what your brain said too. Now, how about if I keep the speed the same, but I increase the radius? So I'm going at a certain speed. Here, let's do it this way. Whoop. Going at a certain speed, and then I want to keep that same speed, but have a longer radius. Whoa, whoa. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that about the same as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Yeah, it's about the same. So as the radius gets bigger, what's happening to the centripetal acceleration? Well, if we look at the math, we see that as this gets bigger, it's in the bottom, that has to get smaller. So for the longer radius, whoop, longer radius, we don't have to have as much acceleration to keep it moving at that speed. Whereas for a short radius, in order to keep it moving at that speed, it takes a lot more acceleration. And so this is the definition of the centripetal acceleration. And for circular motion, the velocity, we're going to be talking about it as 2 pi r over t. Now this velocity, radius is in meters, seconds. So this is our standard unit for velocity. And let's see, this will be, what do we have here? Meters per second squared over radius in meters. So meters squared over seconds squared, all over meters. So one of those meters goes away. That's our standard meters per second squared for acceleration. So centripetal acceleration, meters per second squared, velocity, meters per second, just like normal. But if you think about it, when we talk about things rotating, like an engine or something like that, we don't talk about it in terms of meters per second. So what do we usually use? What unit do we usually talk about when we talk about things rotating? Well, if you have a record player, an LP player, oh, I shouldn't say LP, because that's just long play. So if you have a record player, there were settings. And the two typical settings for a record player were 33 and 45, and they had units associated with them. Those were RPM. If you do engines or a tachometer on your car, it's in RPM. What does RPM mean? What does that mean? So what is RPM? Let's go here. And you probably can figure it out if you don't know it for sure. What is RPM standing for? Let's get rid of that. So, something to do with spinning. P usually means per RPM. Revolutions per minute. Revolutions per minute. How many times does it spin around per minute? Now, we can connect that. That's kind of a speed, right? Because it tells you how fast something's spinning. This is actually what we call an angular velocity. So this angular velocity is not the same as this velocity, or linear velocity, but they have a direct relationship. So what we can do to make that connection, well, let's just make something up. Let's try a toy spinning around, or my fob, let's say. Radius of the spin is 10 centimeters, And I was spinning it at 180 RPM. Maybe I wasn't doing that. That's our sample. What is the velocity of the thing that's moving in the circle? So how do we figure that out? This might look kind of weird, but it's actually really simple. It is, in fact, just unit conversion. If you think about it that way, I'm just converting from one set of units to another, just like meters per second to miles per hour. It's a unit conversion. 180 revolutions per minute. So I want to take that revolutions per minute and I want to convert it to a velocity in meters per second. So I need to end up with meters over seconds. So I can do the easy one first to convert minutes to seconds. All right, I want to get rid of the minutes, so that goes on top. Seconds will be on bottom. And then the harder part. Okay, so 1 minute is 60 seconds. I need to get rid of the revolutions, so that's going to be on the bottom. And I need to end up with meters on top. How do we convert a revolution into meters? Well, if you back up the video just a little bit, how did we find out the distance traveled around in a circle? 1 revolution. How many meters do we travel if we go 1 revolution? Well, in 1 revolution, we travel the circumference, 2 pi r. And so really it's just unit conversion. The only kind of sneaky piece is that you have to realize that 1 revolution means the distance traveled is the circumference, 2 pi r. So 180 RPM would convert to what? I get 1.88 meters per second. Not too fast, but 180 RPM. 180 in a minute means 3 per second. 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. That's doable. So, not too fast, I would say, for a 10, especially for a 10 centimeter spinning radius. Okay, so I'm going to call that part 1 and be done with that.